nanohub.org.
Online simulation and more for nanotechnology.
All right. So we will get started today. What we are going to do today is sort of step back a little and talk about a question that you had about comparing models. How do you compare models, and when do you know one is better than the other? So that's what we're going to do today. And in doing so, we will discuss a whole set of ideas that you may find interesting. Now, since I have not discussed some of these topics before, so I'm not 100% sure about the order in which they can be presented. So you will tell me later that whether the ideas are clear. So that would be the first half. First half or so of the lecture would be on that topic. And in the second half, we will talk about the questions, the comments that you have on the web, and then we'll try to see whether we can answer some of them clearly, right? So those would be the two things I wish to discuss today. So just for an outline, so we'll just talk about that in the introduction. About how do you compare? What is the main question that we are asking today, our main point that we want to discuss today? Let's say you have a set of data points that you have done from experiment, and initially, let's say you had 10 different theories. You have your own 2 theory, 3 theories that you like. You asked your friends to explain the data, or your professor to explain the data. Then they had a few more hypotheses, and you collected, let's say, 10 of them. So out of the 10, as soon as you start sort of fitting the data using the maximum likelihood approach, and then making sure that the chi-square approach and various other things, QQ method, all those methods essentially will take one theory and it will take the data. And then they will compare. Whether the idea being to say that whether the theory and experiment should be thrown away, because it is statistically that cannot match with the data. So let's say after all things being done, you are left with 2 hypotheses that have passed all the tests. Now the question is, of the 2, which one should you take, or which one should you start your experiments with? So that's the goal of today's lecture. And I'm going to tell you about this goodness of fit in terms of adjusted R-square method, the AIC method, there's the AIC, BIC method, and so on and so forth. And then I'm going to talk about this idea about cross-validation. This is a very big topic in statistics, this method of cross-validation. And then the cross-validation and bootstrap would be the other concept that I want to introduce. And they all belong to a class of computer-inspired statistics. So these are all that came from 1960s onward. Once computer became powerful, then these type of things came about. So we'll discuss those things. So here is you have the rate points. And the rate points are the data, and you initially had, as I mentioned, 10 different theories, and now after you have done all the chi-square, QQ, all this case, the Kolmogorov tests, you have done all those, and you are left with, let's say, these two, F1 and F2. Now you want to know which one to work. In some way, they are both reasonable, but you still want to know that what would be a better distribution. Which one should you take? The idea essentially starts with this general idea is called the principle of parsimony. Parsimony, there is simply in a simple way to put this one is to say that the simpler the model which fits the data is better. Simpler model is better. But the main question is, and this has been known for a long time, Even for Aristotle, he says nature operates in the shortest way possible. That was his formulation. Now, George Box is, I should have put George Box later, because Occam is a Franciscan friar, and it's about 12th century. This is a long time, about almost 2000 years, and this is more recent. But they essentially all say the same thing, that George Box says all models are wrong, but some are useful in terms of encapsulating the data. So, and then Occam says that this you may have heard about, that given two or more equally acceptable explanation for a phenomena, work with the one which introduces fewest assumption. So these things are all good. These are all good things to have, but the issue was that before statistics about 1950s, nobody could quantify what does it mean to be simple. I mean, something that is simple to me may not be simple to somebody else. A great mathematician may look at a 25-term equation and say, oh, this is nothing, no problem. And then other person, we have 2 terms, they may say that this is horrible, we cannot take it anymore, right? So we cannot do simplicity in that way. So then this notion of, first that thing came, that is model error and prediction error. That came to be an important quantity. And what it says that, and I'll define it clearly, that model complexity is defined by number of parameters. Why number of parameters? I'll explain that in a few seconds also. So the model error is, let's say this data, I have a few data points here. I copied it from web, so it didn't come through very nicely, but you can see the blue data points. And let's say the data is really a straight line like this. Let's say that was the truth, that if I knew the physics, I would have fitted it that way. But I don't know the physics. So one option for me is one model. Let's say I draw a straight line. That has just one term, because y is equal to c naught. And it has just one term. And it is a very simple model. And so therefore, model is very simple. But the problem is that this data is not being correctly represented, because there is the real thing might have been a straight line. So I have a big error in terms of my model error, because I haven't caught the physics correctly. That is what is called model error. On the other hand, if I take a humongously complicated, if I have 5 points, and if I then have a 5th order polynomial to fit the data, of course it will go through all the points. So in that case, my model error is 0, because model error is at least all the data is being correctly represented. But you can see immediately what's going to happen. At least, let's say this was going straight. At least if you make it as a straight line, it will go somewhere. It will have a huge error. But at least it is going into some right direction, at least, or not getting in the worst direction. A 5th order polynomial, on the other hand, is going to take a nosedive here. And so therefore, when you really make a prediction, you are going to get completely wrong things. So although you fitted the data very well, you actually went into the completely wrong direction, so that your prediction error is huge. So often this is what happens. If your model becomes too complicated, then interpolation becomes very easy. You can interpolate here and here, but your extrapolation often becomes very, very bad. So this is that. So where should you stop? So clearly you have to stop somewhere here. By the way, the prediction error is the blue and the model error is the red. And so therefore you have to stop somewhere here. But what is that intermediate point? How do I know what that intermediate point is? Now, in the calculating the intermediate point, there are a set of formula, but I will explain the physics of the formula in a minute. First, let me introduce you what the formula are and how these things sort of are used. So again, these are the two models that we are thinking about, F1 and F2, and clearly you can calculate the residual between the model prediction, and this is the fit, this is the model, and Ti is the data rate point. and from that you can calculate the residual R. You can calculate that, and then what you can do, so let's look at a set of formula and I will explain it. So the adjusted residual, what it says, that let's say I have n number of data points. I have n number of data points. So how many, what is n? 5. Here I have n is equal to 5. And then I calculate the R square. M is the number of parameters. Now here is something that I want to make sure you understand. If you have a straight line, a plus bx, y is equal to a plus bx, then number of parameters you may consider is 2, a and b. But actually there is a plus 1 here, because there is a third parametric assumption, which is the error is normally distributed, Gaussian distributed. That when you fit a straight line, least square straight line, we know that the error is Gaussian distributed. So you are implying a third parameter, which is the sigma of the error distribution. So in that sense, it is often written as p plus 1. P is the explicit parameter, and 1 is the error parameter. Go ahead.
I didn't understand why you say that there's the third assumption here. Why it's the Gaussian distribution?
So that requires a previous discussion. Maybe I'll come back to that in a little bit later. You can ask me again. This is, you may remember that, do you remember that when we did the straight line fitting? Not the way we generally do, right? We do a regression of straight line. You may remember that this actually is a special class under MLE, maximum likelihood, only when the error is Gaussian distributed on both sides. MLE gives you the regression equation that we learn in school, learn in the undergraduate or graduate classes. So therefore, that assumption is built into the drawing of a straight line. And that's not just straight line. If you do least likelihood of any curved line also, there's the assumption of Gaussian distributed error on either side. So that's an assumption. So that's where plus 1 comes from. If you have more complicated assumption, let's say Pearson assumption about how the error is distributed, then you will put not 1, but you will put 2 or 3, depending on what you need for the error to be described. But let's not get into the details of that. Let's say, so therefore you have to add 1 to account for the error. And then you put it in. So m is here for a straight line, m is 3. Let's say. And so m here would be 3 for a straight line, and so on and so forth. Now you can immediately see what it does. If your m was 1, let's say, that remember the straight line, it was just like that. If it's then you can see that it is all going to cancel, and adjusted residual would be same as the normal residual. The normal residual, it will not be different. But as you are increasing parameters m, then gradually you can see, especially because of this, you are dividing with a smaller number. So your R square may be small. Your R square, because you use more parameters to fit it. So your R square may be, so remember the fifth order polynomial, R square was close to 0. So yes, you can try to do that, reduce R square, but the denominator is now, what will happen if you try to do 5? It will blow, because this is 5, and you try to do a fifth order polynomial. So therefore 5 minus 5, so although it's 0, actually it's a very, very bad fit. So the point is that you have to introduce a penalty for the excess number of parameters you use. So that's your x-axis. Remember the model complexity? That's the x-axis. And if you normalize then with respect to, you have two models, M1 and M2 are the two different number of parameters. You put it in, you calculate the adjusted R square. So that accounts for the fact that how many, did you use a more complicated model or did you use a simpler model? Simpler, the better. By 1953 or 1954, there was this Japanese scientist who transformed the field, and this is called this Eikaike Information Criteria, AIC, and he has a slightly different formula. There is this, by the way, this formula is written in very many different ways, But if you do the substitution properly, it will always get the same number. So you don't be confused if you see in the web different versions of it. ECE intervention criteria, it has 2m. So you can see this is the penalty. This is the penalty, and n is the number of samples. So you divide, because the more number of samples that you have, you can immediately see this will continue to rise. But that doesn't make any sense, because so therefore you have to divide by n and then multiply by n. And if you do this one again, you see this is both all are function of three things: r square nm, r square nm. So there are different formula, and these are what this is. This BIC. Initially, I thought that one guy says AIC, the next guy must say BIC, the third guy must say CIC, and so on and so forth. Sometimes that's helpful, like you have C programming language and all those. So there must be A programming language and B programming, and the C was the best one maybe. But the B really doesn't stand for that B. It stands for Bayesian information criteria. There's a different way to. So let me tell you what this essential story is. What is it trying to do? Assume that you have measured a bunch of data and you have a friend in Mars and you want to send that person that data or about the information. You have done some measurement and you want to send a friend in Mars that data, and that person would try to reconstruct the data. So that's all we do, right? I'm speaking and hopefully you're listening. So I'm trying to communicate through this language, this thing. Of course, it doesn't have to be in this form. I can convert it into a microphone and convert it to a digital signal. I can compress the signal and I can send it to Mars, and they can decompress it, right? And what is then the most efficient way of doing it? So that is where the information theory comes on. So the information theory, what it says that how can I send the information about my data set or my experiment to my friend in Mars? If I have to do it, I have a statistical model. Remember that straight line or the fifth order polynomial and all. So I'll have to gather those parameters. And then, of course, I have the error, Gaussian error and all. That's a +1. I will send those information to the receiver on the side, my friend's phone number or something over on the other side, and that person will use the algorithm and the coefficients to essentially reconstruct the data. The question is that how closely can that person reconstruct my original experiment? The closer they can do it with this minimum amount of transmission, that is what the most efficient information transfer would be. So all these three models, adjusted R-square, AIC, and all these models rely on this principle. Now, how you calculate these are all simple calculation about how using information theory, but that's how from 1950, these papers, some of them probably this is probably one of the top 10 cited papers in the history of science. I don't know, maybe it will be close to 100,000 citations of this paper, right? So he's a big celebrity in the science area. So you get the idea, right? That what is it? That how the model comparison is done. Principle of parsimony. And principle of parsimony quantified in the way of information theory. You don't have to do any of these. If you just put these numbers in Wolfram alpha, it will immediately on the bottom you will see that all these measures are automatically calculated. AIC, BIC, adjusted R square, all those things are calculated because it's so important to measure the data. Now, let me get started with something that is sort of when I first understood it, I thought it was a little puzzling and disturbing. You know how, I should have animated it, but let's focus on this. Forget about the training and prediction for 1 second. Let me assume that I have two data, y and x, and you know the least square. You can fit a straight line through this one, and you can calculate the error and the fit associated with it. We have done that already. We have done it when we did maximum likelihood MLE method or this and that. We always do that. But this is wrong. This is wrong because you are doing two things, double duty. One is you are using the data to fit, and then you are using the data to do the error. That is a no-no. And you may remember, I'll just remind you one time. Remember, I'll come back to this. Remember that we had to take away -1. Why did you have to take away -1 we are calculate sigma? Is because we have already taken the average. We have already used the information once. If we have used the information once, the information content has come down. And so therefore I have a -1. So similarly, I cannot do double duty. I cannot use a straight line and then also calculate the error. That doesn't work. So what is the new way? How should we do straight line fitting and find what line is good? Well, the right way to do it is to take a set of data as sort of quote-unquote training data. Generally, we'll use this thing very soon in terms of machine learning. Generally, it's a 70-30 rule that you take 70% of the data as your training, and the remaining 30% as your prediction. Now, you don't have to take the first 70%. You may take any combination of this. So it's not a necessary that you take. But in the middle of the night, you are trying to draw some green, so it's closer the better. But the bottom line here is that, so what you do, you have two models. Remember, two models sort of fit the data, and you are trying to get the best one. So then what you do, you take the first few training points and fit a line. And you use MLE, whatever you like. You use that. Then you use that one to extrapolate. This was not your part of your fitting process. Now you calculate how far the error is. And similarly, what you do, if you have model 2, you are doing a quadratic. And this was not part of your training. And then you extrapolate. Now it's not a very good quadratic, but you get the idea. And then you will have a little bit more error, right? I mean, you will have a slightly different R square, or you will have a slightly different. Now use this one to actually calculate the previous quantities that I just mentioned. And in fact, you can do various combinations. You can take these 4 for training, these 2 for prediction, or you can take this one for prediction and these 4 training, and run many straight lines and see what the statistical average of those R squares are. And closer it is, better is the chance that you will be able to, by sending this straight line to a friend in the Mars, that person will be able to reconstruct the data, not only in this range, but let's say their friend wants to reconstruct the data at some other point, that he or she has a better chance of getting the data in. You get the idea, right? So partitioning the data, one part for training, another part for prediction, is what is very needed, or is highly needed, or very important. And this is what you will see in machine learning. It will come back over and over again, because machine learning is nothing but a gigantic version of straight line fitting. That's all this is. Don't say it to outside the room. So, but that's what it is. All right. So let me now go to the second point. Remember, this is before computers. You could not do this. How many times you are going to do this point fitting and all? But these days, of course, you do 100,000 of them, the computer will do it in 10 seconds. If you ask people in 1920s to do even 10 of them, the person would quit the job. So that's why it's computer aided is so powerful. Next, let's come to another thing. So it is sort of, you are using double duty. One sample you have, but then you are using the same sample to do double duty in order for both prediction and training. You are doing it. This general principle actually inspired a whole set of ideas. And another one that I will talk about now is called a bootstrapping method. So you know the word bootstrap? Do you know the story of Bootstrap? No? Okay, so I'll tell you a story today also. And then I will ask you whether the story makes any sense. All right. So the idea is that you may remember that this I could have pushed in the earlier one in order to inspire or explain the notion of training versus prediction. But I wanted to show this slide one more time to tell you something more. Remember, in the beginning of the semester, I bemoaned the fact that if you have a population and then you take a sample, you don't know the population, right? You have just one sample and let's say height of all the students in this room. Population is height of all the students in US, let's say. I cannot measure this. And so therefore, for many, many years, people did one sample with, let's say, with some medication, another sample, let's say, without some medication, and then they compared these two samples without ever knowing what the population is. Population was unknown. The strange thing is that changed after the computer, and that sounds impossible, but that's how it works out. So you may remember that, let's say, you have a million, you really have the population, all the students' height in this country, or let's say somehow you have in a giant database, you have them all, and you take 20 of them from the giant database, and you take the average of the 20. And when you get one number, is that number, let's say. And then you do 10,000 of them from the giant database. You do 10,000 of them. And then you will get a distribution associated with it. And what I said before, that, this is sort of difficult because I have only one sample. How do I know what the population average is, how far away it is? Sort of difficult when you have few, let's say now you have 20, but if you had 10, then you have to use T distribution. If you have more than 30, then you have to do Z distribution. All sorts of horrible things you have to know. None of those things are necessary if you do it this way. So this is the idea, and I will explain it slowly, but because it's very important concept. So this is the population. This is the giant database from which all the US students' height are tabulated, which you don't have. What you have is the height of all the students in this room. That's what you have. If you could get 10,000, that would be very good, but you don't. What it says that if you do from the same sample a spatial copy, and that will be called bootstrap samples, spatial, there is a spatial rule for that, and I'll explain that. And if you do from the same one, you are using the same one repeatedly, and let's say you make 10,000 of them repeatedly. Then, if you make a distribution out of the same one, but recreated version, resampling, it turns out you will get a very good representation of the population distribution, which you do not have. So you have not measured the US students' population. Actually, the database doesn't exist. But it will turn out that you just created what the database is. That sounds impossible, right? There are people which are not in the room. How can you possibly do this? It turns out statistically, this has been proven. So this is around 1978 or so, when it was Efron was the first person to do it. But this is when this field started to change. But do you see, before computer, you could not do it. Before computer, how many samples are you going to do by hand? It will be difficult. So let me explain how the sampling works, because this is spatial sampling. The word bootstrap comes from, of course, the strap to a boot. This comes from a story where somebody got stuck in a quicksand. You know quicksand, right? You know quicksand? What is another word for quicksand? Maybe he needs a... Quicksand is where if you walk in, that you sink in slowly. I don't know whether there's any other word. You speak Hindi, so maybe your friends can say what if there's any other word. Is there any other word for quicksand? No. Quicksand is somewhere, looks like a ground, but you sink in as soon as you go there. It's a denser version of water. So there is a story which says that somebody got in there and then was sinking in, and just by holding on to his own boot, he pulled himself up, which is mechanically not possible. Mechanics-wise, it is not possible to pull yourself up. But the main idea here is often used to the fact that when you have a problem, instead of looking for other help, you just look at whatever thing you have and then you solve the problem. So if you have whatever books you have or whatever, you just rely on yourself to solve the problem. So you see, this is in that sense a bootstrap method. This guy is solving a problem that this person was asked to calculate the population distribution, which he doesn't have. Only thing he has is a single sample, and therefore he is using that single sample to solve the problem. Hence the name bootstrap method. So it turns out that it's a very simple algorithm. Let's say you have, from a giant distribution, you have these five data. It's not, I should not say it's height of the students, because there is some minus sign here which will not be good, but you get the idea that there are 5 samples out of many. The trick is the following. You have the single sample. That you have to sort of think about it in your mind as if you have put it in a box. This written 5 numbers and put it in a box. And from that box, you are repeatedly pulling numbers. And so let's say the first time you pull, you pull 0.2, 0.1, 0.6, 0.1, but you see you have pulled 0.1 twice. And then you put 0.5. And of course, you have not put 0.3. So that becomes your one sample. And then you will have to keep doing this, and you do 10,000 times. And then you realize that if there are certain numbers which are a little bit more probable than others, then what will going to happen is that the distribution is going to get sort of closer to that point. So this distribution, because although it's a sample, it already knows within it the essence of the distribution. Now 5 is too small actually. Maybe you are talking about 10 points. By 10, 15 points, you already sort of know. I mean, when I go to a big class, I can just be looking at how the students are doing in a few of the exams. I can sort of tell that what's going to happen to the average of this in this exam, right? So that's the idea. The remarkable thing is that if you really had the entire US students population, and let's say you took 25 and you did 2,000 samples, and then you did a distribution. Let's say you get a sigma of 0.2. This is the giant distribution. That's where you have all the data. Compare that with these two. Here, you have a single sample of just 25 data points. Just one. Here, you may have 1,000,000 data points. And if I did not mark, this is from the computer you have done it by repeated sample. If I didn't say which one is which, you might have difficult time in knowing which one is what. And in fact, it will give you the sigma. It will give you the second moment, third moment, all the various moments would be very close to of course, how many moments can you get? You have n equals 25. So at most you can get 24 moments. So for many, many moments, actually these two will be identical. Of course, which one would not be identical? The one that will not be identical is the first one, because if you have 25, it has some average. Let's say it has a 0 mean from system, but because you have done 25, so the average one will not match exactly, because it is starting with a distribution which does not have exactly that right average. So it will be off by a little bit on the average, but on terms of the shape, which you care about when you want to compare two distributions, what you care about is the shape. In that case, it will be very accurate. You don't have to consult any T distribution book, or you don't have to do any Z distribution. If your sample size is small, it will automatically broaden it. If your sample size is large, it will automatically narrow it. It will take care of all those. And again, one line in MATLAB essentially does all these things for you. Yes.
So why we need to take 25? Like, can we choose another number?
Yeah, of course. Right, this is just
the sample size is 25.
Yeah.
Can I take 20 numbers from this 25? Or like why you should?
I think you can do that. I have not, when I wrote the code, I always did not do it because I had a 25 option. But yeah, I think the number can be different. I don't think there's any.
Number from the initial sample size.
Yeah. It can be different. I think it can be different. But why not write it? It's a 2-line code, right? Generate a bunch of, a set of numbers, maybe 25 numbers, and then just write a little code that samples 20 of them or 15 of them and see how the distribution. I have a feeling that it will be very close. One thing you have to be careful about, if you take 20, then when you do the sigma, you have to divide by square root of 19, 20 minus 1. If you do 25, then you have to do square root of 24, which is 25 minus 1. That you have to do, but other than that, I think it should work. Now, I want to wrap up this thing about a distinction between parametric versus non-parametric bootstrap. Another very important thing for model comparison. Remember, that's the goal of our lecture today, how to compare two models. And I want to explain this one to you. Yeah.
So in the previous slide,
yes.
If the first, the sample that you have 25, even if it's biased, you will have the same second moment and third moment?
Similar, very similar. Because, if you look at this, you have actually, for this particular one, I had 0.18 and the real one is 0.2. But remember, the real one you don't have. So therefore, 0.18 is an approximation of 0.2. Right? So that's what this one is. All right. So what I said here is non-parametric. Did I assume anything about the distribution, where it came from? Is it weighable? Is it log normal? I don't know. We just sampled and did multiple sample, and whatever comes out of the distribution, that's my distribution. So this is called a non-parametric one. I didn't have any parameter in terms of creating the distribution. So 7, let's say I have 25 experimental point, and then I created a million, as if I did a million experiments, and I have that information. That's very good, right? But then there is this second issue that you can also do, which is called a parametric version. By parametric, I mean, let's say you have 25 points, and you know that it could be weighable or it could be log normal. Let's say you have narrowed it down into the final 2. Now you want to know how robust is the fit. How robust is the fit. So what you do, you take this data point, and then you do a maximum likelihood, just like what you have done before, normal fitting. And then that will give you, remember that if it is a weighable, then you are going to get 2 parameters, eta naught and beta naught, because weighable is a 2-parameter distribution. So you are going to get 2. Then what you do, let me show you with an example. I think that's first let me show you this one, and then I will go back. So let's say that this is your original data. These were the TI. First device failed here, second device, third and fourth devices failed here, and so this is your distribution. And from that, you have fitted the original weighable. Now you have a line. Now from that line, choose any 5 points. Any 5 points. So you may, because on this line you may choose. So if you choose, let's say you have chosen this point, and you have chosen that point, and you have chosen that point, randomly. Choose 5. Then if you choose those 5 points, now you have a new distribution. Right? Based on the new 5 points, based on the parametric thing, because any 5 points is based on that. Now you fit it again. If you fit it again, you will have a new weighable distribution with eta 1 and beta 1. Right? You can either stay with the blue and then again sample another 5 points. That will give you eta 2 and beta 2. And very soon what you are going to get is a distribution of etas. That what is the range of eta that can fit the data, and what is the range of beta that could fit the data. So this one, for example, is eta naught, and this one is, for example, is beta naught. But you have all the uncertainties associated with it. You don't need a humongous formula, because so often, as I told you, fish in the river problem, you cannot calculate the error rate so easily. I mean, that will be 2-page long formula. But if you use this method, you fit it first, the fish in the river problem, and then do repeated sampling, and then you keep sampling, making new fits. That will give you the deviation, that what is the error range associated with it. Is it clear? more or less. And so that was what I was saying in here, that you generate synthetic based on the parametric distribution. Take the blue line, take another 5 points, fit it eta 1, beta 1, take another one, and then that gives you can do, let's say, 5,000 of these. And that gives you the bound, error bound of how range of eta and beta that you might have. So actually, there is a Nature paper, I have it in the tenure rate in faculty. In this country, there is a big issue about often the women faculty are very difficult to hire because there are so few, but then also the rate at which they don't go for tenure, meaning that after 1-2 years, many times people have to leave. So many of these distributions have Weibull type distributions. So people that have done it, and it's very important, you make policy out of this. So therefore, if you have so few data, it's not like you have million pieces of data, and you have to make robust policy based on how to sort of retain people. So in that case, often people use this statistical technique to essentially devise policy and all. So I have some references. Polling is another one, as you can see, is very important. What is it? 530? 538? Is that website? 530? 538. So in the polling 538, it is a NetSilver's website. And so many of these techniques that I'm telling you now analyze those error distributions. Who will win, Democrats or Republicans? What is the probability of winning? What do you think? They are using Gaussian distribution? Not any chance. All right. So to summarize then, if the physics on his side, then it's called a prior, meaning that then you already are starting from a good point. In some way, you have a strong bias in that case. But often people, when they think their physics on their side, physics is not really on their side. What is on their side is a bias. They think, or they hope that if the theory is correct, they can graduate. So therefore, that's really not physics on their side. That's really bias on their side, and which is very dangerous. But if the physics is not known, or if people have doubt, in that case, this computer-based model, all started from 1950s, is a very powerful technique. These are all one lines in your MATLAB. You're listening to all this, but it's not really important. The important thing is to use them. Just use one line in the code when after your analysis is done. Just have a little analysis code of a few lines. That will be good. I explained today that how to sort of balance between decide between two models which have passed all other tests, but you are just comparing between the two. So what is the principle? Principle of parsimony. The simpler the better, quantified in terms of AIC, BIC, and all those models. And this Bootstrap and Monte Carlo approach, why is it called Monte Carlo? Because you're generating random samples out of that. That's why it's also called Monte Carlo. So the Bootstrap method, and again, using one piece of data, one piece of good data. You see, this disconnect between small and large data is not so big, because although the data is 25 points, you are effectively generating 1 million. And in some way, this little data, if you have done it carefully, not random data, you have done it carefully, actually that big data generated from here contains more information about the actual distribution than if you just took a million random data, right? So therefore, this disconnect between small and large data is not very, give me 1 second, is not very big. So there are you can see this is a very active field. When people write papers like, what is it? No freelance theorem for search. Then note on no free lunches and cross validation. When people write these topics, that means it's a highly exciting topic in the field. And many of them have thousands and thousands of citations. Because once you can prove one of these, everybody uses it. And then there's this paper I like very much because he is the pioneer. A lazily look at bootstrap, jackknife, and cross validation, because these things are all connected. But although he says it's a leisurely look, it's not so leisurely that you want to read it in your vacation. All right, there are other things you should read a little bit in order to get the essence of it.